So in this video, we're going to talk more about the single source shortest path problem that we introduced in lecture. And to start, we're going to look at the unweighted version. So we still want to compute this distance function here, but now the problem's slightly easier because we don't have to worry about general weight functions. Just the weight of the path is going to be its actual length in terms of the number of vertices. So we just care about the number of vertices in the path for the unweighted case. So actually the optimal thing to do here is just to use breadth first search. To remind you all of what breadth first search is, consider this grid graph here and say your starting node is S right there, which is 13. And the way breadth first search works is it maintains a queue and it starts by visiting the start node S, and then it'll move one edge, say up, it throws 8 on the queue. And since queues are first in, first out, 8 will be the first thing we pop off the queue when we pop off stuff. So the next thing we do is we move to 14, say, we throw that on the queue. We move to 18, we put that on the queue. Then we move to 12, we put that on the queue. So at this point, we've essentially completed the first wave. So we've hit all of the nodes of distance 1 from S, and now we're going to repeat the process. So we remove 8 from the queue, and that's where we're going to now start. So now we're going to look at the neighbors of 8, which will be 3, which we'll throw on the queue. Then it'll be 7, say, and then 9 is at the very top. So those are the next ones we're going to visit in the second wave. Now we pop off the queue again, so we lose 14. So now we go to 14 over here, and we look at all of its neighbors. So we add 15 to the queue and 19 to the queue, but we don't add 9 to the queue because it's already on there. So we've already marked 9, or we've at the very least decided we're adding 9 to the queue. So at this point, we're not going to add it again. And this process continues in waves. We keep looking at the current, what's called frontier, which are all these nodes right here that we're going to visit next. And for any node on the frontier, we extend the frontier by 1 level by adding its neighbors to the queue. And so we'll slowly move farther and farther away from S, 1 step at a time, until eventually we get this entire breadth first search tree, which if we follow the blue highlighted lines, will eventually extend in this kind of shape until we've hit every node. So that's what breadth first search is doing. And if we looked at the formal pseudocode, essentially it's just whatever first search with a stack, or not a stack, with a queue. So this is the algorithm. We start by adding S to the queue. Just as we did before, we started with 13, and then we slowly expanded. So we take something off the queue. So this will be at the bottom of the queue. We take it off, and then we go through all of its neighbors. And for each neighbor, what we're going to do is update this distance function. So what I described above is just how we're going to move throughout this, throughout the graph. But while we're doing that, we're also keeping track of the distances. So in particular, the distance of S starts at 0, because of course the distance from S to itself is 0. We don't need any edges. But then for every neighbor of S, well, we're going to add 1 more. So when we pull U initially, it'll be S. And then this says the distance of all of its neighbors will be the distance of S plus 1, which is just 1, which makes sense. So up here, this would say that 8 has distance 1, 14 has distance 1, and so on. S has distance 0. And then continuing this process, the distance of 3 would be 2, the distance of 9 would be 2, and so on. So not only are we growing what we're looking at, but we grow the distances as well. And so that's the idea. And in particular, if this distance would be an improvement, in other words, have we marked v yet or not? If we have already marked v, then this distance will be smaller. So that's the case of 9 before, where we already visited 9, but we had the choice of also going through 14 to get to 9. But since we already added 9 to the queue, this would not update the distance function, because essentially it's already marked. In other words, the distance function dist of v was already defined. So initially you think of these distances as all being infinity. That's the initialization step. So the first time we visit the node, we update its distance to be its parent's distance plus 1. This is the parent. And we continue this process recursively. So the question is, will these distances actually be the shortest? So intuitively, we'd think yes, because we start at S, and we just move one edge at a time. So naturally, we couldn't really get to 7 faster than to take these 2 edges, because we're moving just one step at a time. But we need to prove this formally. So to prove it formally, we're going to use a definition of waves. So we can think of waves at a high level as just, we're now at k edges away from S. So as before, we moved one edge away from S, processed all those nodes, then we moved 2 edges away from S, we processed all those nodes, and it kind of evolves in the same way, where we have these waves or phases where we're processing things on the frontier of the same distance away from S. And so that's the idea behind the algorithm, is the distance should really equal the same as the wave number. So what's a wave? Well, the 0th wave is just the set of S, because at the start, we haven't done anything yet, it's just S. And the kth wave recursively is defined as the set of nodes added to the queue by nodes in the k-1 wave. So for example, the 1 wave, this would be equal to the set of 8, 14, 18, and 12. Because in the very first step of the algorithm, once S was popped, which is from wave 0, all of these were added to the queue. And similarly, the 2 wave would consist of, say, 2, 9, 7, all of these nodes that were added from nodes in this set. So we dequeue nodes in this set, and those add neighbors, and those neighbors go into the next wave. So again, it's this growing idea. We keep growing the frontier and updating the distances as we go. So we say the k wave ends when all the nodes in the k wave are removed from the queue. So at the point when all of these have been dequeued and processed, we say that one wave has ended, because now we're only considering nodes of distance 2 or farther away. And the key observation is at the end of the k-1 wave, the queue contains exactly the nodes in the k wave. And this should be wave, not way. And you can prove this easily by induction, but I think it's pretty easy just to see by thinking of the process. So now to prove this algorithm really is computing the optimal distances, let's consider this lemma here. So for any v in the k wave, we want to show that the true distance from S to v is equal to exactly what we computed, the distance of v, and it's also equal to the parameter k in the k wave. So this is just confirming our intuition that as we're growing and get one edge farther and farther, that actually is the true shortest path distance. So to prove this, we'll use induction on k. So let's start with the base case, k equals 0. Well, the only thing distance 1 from, or distance 0 from S is S itself. So in particular, the 0 wave, by definition, is just equal to S, and we initialize distance of S to be 0, and that in fact is the correct d of S. So that's correct. So that part's easy. Now for the inductive step, we're starting at an arbitrary k-1 or a k wave, and we want to prove that these distances are correct. So we can essentially do this by contradiction. Suppose that there was a smaller number k prime, and the distance from V to S was actually k prime smaller than k, where k is in the V wave, or sorry, V is in the k wave. So let's say that was the case. Then in particular, there exists a path from S to some U and an edge from U to V such that the length of this path plus 1, which is the length of this whole path, this whole thing is exactly equal to k prime. So in particular, this was the case. We know by the induction hypothesis, so since the length of S to U is smaller than the length of S to V, because it's a subpath, the induction hypothesis will imply that U also satisfies the properties above. So because this is the shortest path, U must have been in the k prime wave, since by the induction hypothesis, d of U is correctly equal to k prime, well, k prime minus 1, because it is 1 smaller than that. So we know U was in some earlier wave, which is the point. Now the question is, if U was in an earlier wave, why did the algorithm set or place V into the k wave? So when U was DQ'd, which always happens before V would be by the observation so when U is DQ'd, by definition of the algorithm, we take off U and we immediately would look at all of its edges U to V and then update those distances. So by definition, we have here that there is an edge U to V. So when alg considered the edge U to V, it would have set the distance of V to be the distance of U plus 1, and we know this is exactly correct. This is the distance of U plus 1, which equals k prime. So the algorithm would have set the distance to be k prime, but we claim that actually it was set to this larger k, and this is a contradiction. And so that's the proof complete. So the idea here is, inductively, we're correctly getting the distance of these nodes. And so in each wave, we move one more step, we're getting the correct distance for those nodes. If there was a better, shorter path directly, well then a previous wave node would have added this node instead of this later wave. So essentially, the earlier waves will always grab shorter nodes. And so that's the proof. So the analysis we've already seen, it's the same as whatever for search. So it's O of E plus E. But the main point is that we can correctly construct shortest paths in unweighted graphs by using breadth first search.